I'm just going to talk a little bit about introduction to NMR. We'll go through a little bit of theory, not much, and then some practical applications, and then what the ARC has, and then kind of what the future will be for NMR here. Okay, so hold on. Okay, so for NMR, if you don't know what it is, it's a structure determination tool most chemists use. So if we look at the periodic table, it's kind of color-coded for nuclei that are NMR active. The most popular ones are typically spin 1/2, so those are the ones in yellow. Integer spins are green, that's only nitrogen, and then quadrupole nuclei, which have a half integer, are all of the blue ones. So there's quite a few nuclei that are active. It doesn't always mean that they're the easiest nuclei to observe, but they are active. So the most common nuclei are kind of the ones listed here, mostly biologically relevant. So proton being the most popular, carbon, nitrogen, oxygen, fluorine, aluminum, silicon, and phosphorus. So kind of the main takeaway here from this slide is really the natural abundance. So that's this kind of category here. So proton is basically 100% natural abundance. There's a couple other nuclei, fluorine, aluminum, and phosphorus. The rest are not. So you kind of, it's kind of a low sensitivity technique in those regards, but we can still observe them and kind of get good data for those. Okay, so let's take a look at a basic molecule. So that would be kind of just water. So what's happening for this molecule as far as NMR is concerned? So if you look at this proton, each nuclei has a spin moment. And so inside of a magnet, it behaves as a small quantum magnet. So that's kind of the key for NMR. So what's really happening? So you have all these nuclei, they have all these different spin orientations, but once you put it in a strong magnetic field, you have orientation with the magnetic field or against it. So this is only for spin 1/2 nuclei. All nuclei will do this, but when I talk about the energy levels, this is for spin 1/2. So what happens for spin 1/2 is you have a Zeeman energy that splits the energy level of the spin. So that's this transition here with this energy. So the transition between the two levels for spin can be, you can introduce an RF pulse that will allow you to transition between these two energy levels. So relaxation is what gives NMR its signal. So unfortunately, the population difference between these two energy levels for NMR is usually quite low, which makes it a very low sensitive technique. So if we go back to this picture, we're in a strong magnetic field. If we have 2 million spins, 1,000,001 will be aligned with the magnetic field, and 999,909 will be against it. So you can see that this is very, very low sensitivity. So luckily, the most popular NMR nuclei is hydrogen. So it's 100% natural abundance, so kind of can get around this issue. So what does NMR do? So somehow we have to kind of push the spins between these two energy levels. So they don't really want to be in these non-naturally occurring energy levels. So once you push the spin to the other level, you flip the spins, it will relax down. So when it relaxes, then you get your NMR signal. So that's usually quite low kind of detection. So that's why you have to amplify the signal with a console and to detect. But so once you push them up, it'll relax, and then you can detect your signal. Okay, so from a practical point of view, kind of what's happening. So this is your NMR computer. This is a console. This is what you call the front end. There are cables to the probe. This is the superconducting magnet, and then this is where your sample ends up inside the magnet. So the probe meets the sample at the center of the magnetic field. So this center is actually quite small. It's millimeters small of usable magnetic field in this huge NMR magnet. So kind of where you start is you start at the computer, you tell it what you want it to do. So whatever sequence you're looking at, if you're looking at proton, you pick the proton experiment, you tell it, yeah, that's what I want to do. So it gets all of those things ready for you, and then kind of sends that information to the console. So the console is in charge of generating pulse sequences, the timing, your lock signal, your shimming, the power to everything. Everything kind of lays inside of this console. So once that happens, then it kind of passes through the RF front end, which has a preamp and other components that are important, but we don't really talk about. And then there's a cable to the probe. So once it reaches the probe, it passes through the coil where the sample is kind of inserted. So then this is kind of where you can excite your nuclear spins. However you need to for whatever pulse sequence or nuclei you're looking at. And then those nuclei will resonate. And once they kind of relax back, the weak signal comes back through the same cables to the front end and then back to the console. So the console then will detect this tiny signal and then amplifies it so that we can actually do mathematics Fourier transform and look at the signal. So once that happens, then you go back to the computer and you can do all of your post processing things. You do your Fourier transform, you do your integration, your peak picking, all of that stuff happens kind of on the computer. Yeah, so that's kind of what happens for NMR in a nutshell. So why is NMR important? So most people use it for structure determination. So I'm going to go through a sample, kind of how do you take your NMR tube, what experiments do you use, what do they mean, and how do you get to a structure? Okay, so kind of the strategy for this is you would do your protons first, and then your carbon spectrum, and then any other nuclei that could possibly be in your compound, phosphorus, chlorine, nitrogen, any of those kind of techniques. And then you would do 2D spectroscopy, an HSQC and or an HMC QC, a TOXI, which is a proton correlation experiment, Alcozy, which is a 2D proton correlation experiment. They're slightly different. I'll explain that later. And then kind of for how a molecule connects together, you do long-range correlations, which is an HMBC. So you can use that between proton and any of these X nuclei that you have in your material. Kind of the last experiment you would run would be a NOSI or a ROSI to get stereochemistry and 3D structure. So kind of we'll get started with that. So the sample that I used is called Taxol. It's an anti-cancer drug. Here's the chemical structure or the formula and the molecular weight. The concentration for this particular experiment was 5.2 milligrams and 600 microliters of chloroform. The system that was used, so this data is pretty old. It's a 500 4-channel system with pulse field gradients and waveform generators, which nobody actually says anymore. But it's basically an ANOVA console, which was, if you have ever run on the 500, that was kind of that console. So that's kind of where this data came from. So it's pretty old, but it still shows the point. So the first experiment, which takes about a minute, is a proton spectrum. So most people, this is pretty familiar to them. You have a chemical shift range from about 0 to 12 ppm, but there's nothing kind of way out there. So you integrate your peaks. This insert here is really just to show that for proton experiments, you do have a proton-proton coupling that you need for true structure determination. If you don't know what the structure is, those J couplings can tell you things about which protons are connected to which protons. So that's really all that's there for. So that's your protons. And, what does that really mean? So there are a bunch of tables and there's a bunch of prediction software around, but basic on the chemical shift, you can get an idea what type of proton that is. So if you have an alcohol, you have an aromatic proton, whatever the case may be. So kind of when you get going, you start with your protons, you can kind of, determine which chemical shifts are which, and then you would move on to your carbon. So this is the carbon spectrum for Taxol, and you can see that this is the CH3 region, CH2, CH, the aromatic region, and the carbonyl region. So same for proton. For carbon, you have these chemical shifts that give you information about structure. So I kind of gave you broad strokes before, but there are a bunch of different carbons that kind of can overlap, and it really depends on your molecule, what makes sense. So at the end of the day, you run a proton 1D, a carbon 1D, you end up with a list of chemical shifts and their integrations. So this is kind of the beginning of putting everything together. So once you have your proton 1D, your carbon 1D, the next step is to take a proton carbon correlation experiment. So that's typically an HSQC experiment. So what does that really mean? So for this carbon attached to this proton, you would see a cross peak. This cross peak is driven by the J coupling on the bond. So these are through bond experiments. So this is a one bond experiment. So this carbon to this proton, this proton to this the CH3 or these three protons here, this carbon to these two protons. So those will end up with it, what they call twinning. But one is from this proton and one is from this proton. So they are color coded for a reason. HSQC is an edited experiment. So red typically is CH and CH3. Blue is CH2. So that helps you decide which carbons are which. So if we take a look at the data, kind of this is a small snapshot of what you see. I'm not going to go through every single carbon and every single proton. That would take quite a long time, but you kind of get the idea. So you have a proton on this side, a carbon on this axis, and when you have a cross peak, those carbons are connected to those protons. So this is CH2 because there's your two protons. And then you have some CH3s that are probably way up here and some CHs that are around here. But you can kind of get a feel for what your protons and what protons are connected to what carbons. So the other experiment that you can run for HSQC and was run on this molecule was a proton nitrogen correlation experiment. So there turns out there's one, sorry. Okay, there's one nitrogen in this molecule and it's attached to one proton. So that's this cross peak here. If you blow it up, it just looks like this. It has a splitting pattern. So that's an easy way to get around taking a 1D nitrogen, which can be very difficult, is to do a 2D experiment. So then you get a little bit more data. You get the 1D, of course, because you're collecting the 2D, but then you get which proton it's connected to. So this nitrogen is connected to this proton, so we can eliminate that proton from our list of proton chemical shifts because we know it's attached to the nitrogen. So we already accounted for that one. So at the end of the day, the HSQC kind of gives you 26 CH pairs, the one nitrogen pair. There was positive peaks. There was 17 CHs, 6 CH3s, and there were negative peaks that were 3 CH2 groups. So what was absent in the HSQC are the 15 quaternary carbons and the one exchangeable proton, which we picked up in the nitrogen experiment. So that's kind of why that one was done. So at the end of the day, for 2D HSQC, we know which protons were connected to which carbons. We know the nitrogen proton that was connected to the nitrogen. We know which ones are CH2, which ones are CH3, which ones are CHs. And from the carbon, we know which are left over have to be the quaternary carbons. So that's kind of the process of elimination, how you kind of go through this data. So the next experiment you would run would be a TOXI experiment. So it's a total correlation experiment. So it's a proton-proton correlation experiment. So for this experiment, there is a diagonal down the middle of your data. It will always be there. It's that proton's correlation to itself. So it's kind of a way to ground yourself in a 2D proton-proton correlation experiment. So the idea for a TOXI experiment is you let the signal go anywhere it can go. So this is also a through bond experiment, but you can go from, like, let's say this proton through this bond, to this proton, and you would see a cross peak. The nice thing about a Toxie experiment is that it does not go across heteronuclei, meaning oxygen or nitrogen or some huge like electron drawing element. So oxygens are huge like that. So it takes a lot of energy to go across these bonds. So you would never do that. So Toxie helps you kind of piece together, okay, I've got this substructure here and this substructure here. And so that's kind of the big takeaway from Toxie. So if we look at a subset of the Toxie data for Taxol, you can look and see that the green lines are protons at 8, 7.5, and 7.4. So those protons are connected to one another, but they're at least 3 bonds away. They're not connected to anything else. So you don't see any cross peaks, like you wouldn't see a cross peak here. So that's kind of one subset of structure. So if you look at the blue line, this is 7.41, 735, 728. So again, these blue ones are connected to each other, but not to anybody else, not to any of the other cross peaks. And then the yellow one here in the middle, this is the same. So these guys are connected to one another. So this kind of helps you get these little pockets of substructure. And then the other experiment that you run for proton-proton correlation is called a cozy experiment. So it's the same idea as a Toxie experiment, but it's usually 1 to 2, 3 bonds. Toxie can go maybe 4 or 5 bonds, but the idea is the same principle. You have a diagonal, that's the correlation to itself, but you kind of can walk around a molecule. So if you start at this chemical shift, which is 4, you have a cross peak with proton that's number 3. And then back to the diagonal, you can go back up and 3 goes to 2, back to the diagonal, and you can come back down and mirror it the other way. So that's kind of how a cozy works. So for this set of data, I'm just going to highlight one pocket of the cozy data where you have this is your kind of known structure from the Toxie and your HSQC. So the HSQC is giving you the clue that these are CH2 protons. And so those are kind of easy to pick up because they kind of are geminal pairs is what they're called. So if you look here, so this is the proton axis, this is the carbon axis. If we look at 35, so that's this guy. Oh, it's not there. What's this? Oh, that's the same. Oh, I got it backwards. Okay, so this is the cozy. So this is proton. So that's these protons. Sorry. So this is the biggest proton is 4.8. So that's this guy. If you go over, this is 2.5. So that's this guy. If you go up to this and over, then the 2.5 goes to the 1.8. So that's this to this. And then you go back up to the diagonal. So that's kind of how you put this part together. If that makes sense. So then you know, okay, I have all of these guys and they're connected to these guys. For these chemical shifts are coming from the HSQC, and these kind of are how they're oriented. They have to be put together this way based on the cozy. Okay, so from all of the data we have thus far, we have all of these 9 substructures. And so now you have to determine how you're going to put them together. So typically that's an HMBC experiment. So if we look at this carbon, so carbon 3 here, you will see a cross peak, a carbon to a proton cross peak at C4, that's H4, at the 2, that's H2 and A, these 2, and then at 1, these guys, and then at 5, this one. So this is all through the bonds. So it's the J coupling on the bonds. So this looks like it's a through space, but it's not. It's just showing you kind of where they go. So then if you look at C4, you don't have a cross peak at H4. Those are filtered out because that's the HSQC to kind of help you you look at the data a little bit better. So if we look at the HMBC for Taxol, this is kind of all of the cross peaks. So you can tell this can get quite confusing. If you don't filter out the HSQC, you would have a whole nother set of cross peaks that are just from the single bonds that you've already looked at that data. So that's filtered away to help you kind of really zero in and determine which protons and carbons are long range connected to one another. Okay, so I'll just look at one kind of three subsets and how they connect together. So if you look at the green that's up here, so the carbon is at 167.1, and you see a cross peak at 6.9, and you see a cross peak at 5.7. So that's this guy to this guy and this guy to this one. So these have to be connected, kind of based on how far the experiment goes. Okay, so if you look at the red one, that's this one. So this is an aromatic carbon connected, or proton connected to this 55. So 55 and 7.4, these guys are connected together. If you look at the blue, so then you can see that you have a carbon at 167, and it comes back to this side at 7.6. So that's this carbon or this proton, and then at 8.01. So that's the other carbon or the other proton. So based on how they're kind of, how you kind of see cross peaks, you can determine that these three subsets have to be connected to one another in a particular fashion. Okay, so when you go through all of your data, you end up with a unique chemical shift for every proton and carbon and the one nitrogen here in your kind of system for Taxol. So that's great, but if you look around, there's a bunch of asymmetric carbons. So how do these carbons kind of orient themselves in space? So that's kind of where the nosy and the rosy come in. So the nosy and the rosy are exactly the same experiment. One happens in what's called the rotating frame, and one does not. So the rosy happens in the rotating frame, the nosy does not. So why does that matter? So typically for small molecules, the nosy is a little bit better. And for large molecules, the rosy is better. But it's not set in stone and there's no like magical cutoff. So typically you just try one and see if it works for you. And if it doesn't, then you try the other one. But this is actually a through space experiment. Kind of the limit is 1 over the square root of r to the 6. So you have to kind of take that into consideration where you're looking for long range kind of proton-proton correlations. There is a limit. It's about 5 to 8 angstroms, and the NOE scales as 1 over r to the 6. So you're not going to see something, you know, I mean, 8 angstroms is really pushing the limit on the systems we have here. Maybe on a new spectrometer at high field, probably it would be a little bit easier. Okay, so the idea is this is kind of through space. So you can start to kind of understand whether this is kind of a chair or if it was a boat shape based on how intense your cross peak is. So for this is a proton-proton correlation again. So you have a diagonal. So these are the protons that correlate to one another. They're red here, so it's color coded so you know, and then the blue are the NOE cross peaks. So for Taxol, this is kind of what the data looks like. And so it's pretty confusing, but you can kind of step through it one plane at a time. So if we look down this kind of bond and the one proton here at 4.7, so you notice that you see the cross peak to itself, but you see a cross peak to 5.72, which is this peak or this proton. You see one at 7.4, that one, and you see one at 3.48. So that's this proton. So based on the intensity, you can tell how close they are to one another. So this one has more intensity than this one, than that one. So based on that, if you look down the plane, you can tell that this has to be the orientation of that bond based on the NOE data. So you will go through this for every a kind of slice of proton that you see and make the same kind of determination for every carbon that had the possibility to be asymmetric. So it's quite a tedious process, but at the end of the day, you end up with the secondary structure of your molecule. So based on these two boxes, this is what's known. This is the only relatively known configuration of Taxol. So that's kind of what NMR can do for you. And this is just one way to get there. There's hundreds and hundreds of experiments to run, but you have to pick the ones that kind of work best for your molecule. Okay, so that's all for that. So then I was going to go through kind of the arc and what we currently have. So the arc is split between Bruker and Barium. So we have 3 Bruker systems currently. 2 of them sit in CAMR. So that's the US 400 and what people call the walk-up or the ASC 400. So these systems are almost identical. They have a broad-banded probe. The only difference really between the two is the sample changer. And then there's a 400 in the basement of the chemistry building. So that system has what's called a Prodigy cold probe. So it's a nitrogen cold probe that feeds liquid nitrogen to the electronic components, including the preamp. So that actually helps with the sensitivity of the probe. So the probe is very highly sensitive compared to kind of what's over in the other buildings. So that's great for if you have a small amount of material, you spend 6 months making some, perfect protein or what have you, and you only have like 0.5 milligram of material, this is the probe where you would want to do your structure characterization because you get the most signal per scan. So then on the other side of the coin, we have barium or adjuvant. So there's a 400 MR. That's this guy that's in the basement of chemistry. So it's a high throughput system. The sample changer holds almost 100 and, it does variable temperature and that one's fine. And then there was a 500 and a 600. Both of them are now decommissioned, so they are no longer. So kind of what the plan is, we went after an NSF proposal with Nancy Levinger for 600, and it actually got funded. So we will be getting a new 600. It's a 5-channel system with extended VT. It has a 60-position sample case, a Prodigy TCI probe code, so that's an HCN probe, and a broad-banded HX liquid probe, and it will have solid-state NMR capabilities with a 4 millimeter solids probe. So this is fantastic. So hopefully we can get this, they're saying maybe 9 months out once you order. So it will be a while, but it will be here. So then the other NMR that we actually got funded was a basic 400 system to help with the kind of workload in ChemR. So the 2 systems that I mentioned in ChemR are basically at capacity. So this is a basic NMR system. It will have a 60 sample case, an HX probe, and we also got what Bruker calls a HelioSmart. So it's a liquid helium it's the helium recovery system. So it recovers the gaseous helium that boils off from the magnets, and it takes it to the high pressure cylinders, which we can kind of connect to our current recovery system and liquefy to liquid helium. So this is really helpful to kind of keep our, footprint of liquid helium down. It's a non-renewable resource. So once you use it, it's gone. And as time goes on, allocations happen and you can kind of go down to 0 allocation. So this kind of helps us be a little bit more self-sufficient. Typically for helium recovery, you can recover 70 to 80% of the helium. So this is kind of a good step towards getting all the NMRs on the recovery system. And then kind of the last thing I wanted to mention was NMR metabolomics. So this is kind of a project that Claudia Boot and I worked together on. So these were her samples. They were soil samples from the Arctic, and kind of she did some sample prep. I'm not really sure about those details. You can ask Claudia about those. And then we ended up kind of working through their NMR experiments to get them optimized for her data. And then she was able to collect I don't know, 30 or so samples, and then go through the metabolomic software and determine, which ones were different and how. That's not really my area, but we are offering this service now, but it's kind of Claudia and I working together where she kind of handles the metabolomics part, and I can help you kind of get your NMR kind of situated and make sure it's the best that it can be for your samples. Yeah, so that's all I have for today. Are there any questions? Kind of went fast.
Just post them in the chat if you can't speak. Any questions? Michelle, can you talk a little bit about what added capabilities the 600 will bring us and what it will allow our researchers to do more of?
Sure. So a Prodigy TCI cold probe is an HCN probe. It's not what you call broadbanded. So this will help do structure determination for tiny amounts of materials, mostly biologics. But you were able to do 3D experiments, which we can't do now. So you could do like a proton nitrogen carbon correlation experiment, which we can't do at all right now because we don't have that system. The liquids probe, the HX probe is the standard liquids probe for, basic liquids, solid state NMR. So that's something I don't think that's been here for quite some time. So this allows you to take a solid sample, put it in a rotor, and you can collect what you call bulk, you get bulk information about your solid. So it's the same idea as other NMR, liquids NMR, it's just a solid. So you don't have to worry about dissolving your sample. You can get it back. You can use anything that is solid and not magnetic for obvious reasons. But yeah, it's a great tool for polymers or biologics, people who have peptides attached to lipids, or you have this weird kind of mix of maybe tissue and other materials. So all of those things can go in a solids rotor. You spin quite fast to get rid of some of the dipolar couplings that kind of create a problem, and you spin at something called the magic angle for other quantum mechanical reasons that I won't talk about. So all of that helps you kind of with your solid state NMR experiments. So that's kind of a big thing. We don't have that now. Yep.
I see Delphi's icon blinking, but I'm not sure if
I'm
Delphi has a
here.
question. Oh, I saw something blinking, so I thought you had a question, but
No, I didn't have a question. I was just thinking if it is compatible to the magic angle that we had before.
Same magic angle. Yep. Same
Same
one.
magic angle. So
Yep.
will there be a lot of time involved with changing the probe and all that?
Yeah, so that's kind of a tricky situation. So the cold probe is by far the hardest probe to change out, and it's not like it's a hardware thing, it's a time thing. So you have to break vacuum on the probe, you have to warm up overnight. So that's at least a day to get it down. When you want the cold probe back, it's a 20-hour pump down. So it's
Yeah,
almost
that's what I
2 days.
thought.
Yeah. So the idea really is we would have kind of a matrix of which probes we would use. And kind of the default probe would probably be the cold probe. And then every month or two, kind of reach out to the user group and see, okay, do you have a solid sample, or if people want to use the liquids probe, and make the change every couple of months. If there's no samples for solids, then we would just leave the cold probe. Makes no
Okay,
sense to kind of just take it out for no reason.
right.
Yeah. So that's kind of, we'll have to come up with some sort of matrix that kind of works well. I mean, maybe we just run the cold probe for 6 months and then run the solids probe for 2 months, and then everybody who has solid samples just waits till then. It doesn't make a lot of sense to take it out for one solid state sample.
Yeah, and I was also wondering why didn't we go for a 700 rather than 600? Was it a lot more?
It probably was a lot more, but it was really the idea was 600 is kind of, it gives you enough of a boost without kind of becoming like a $4
Okay.
million system. Yeah,
Yeah,
it's pricey fast.
all these grants have upper limits.
Yes, they do. Where
And
is it
broker,
going to be housed?
Do you know where the 500 was?
Yes.
Yep, we're going to put it right
Okay.
there.
All
Yep.
right.
Hopefully, we're going to scooch it over in case we can get another 5.
any other questions? Okay. Well, thanks, Michelle.
Thanks,
Sure.
Michelle.
Anytime.
And keep us all updated when that purchase order goes out.
Yeah. Hopefully
It's a
this
big
year.
one. It's a good year for NMR, so all super excited and yeah, some much needed added capacity will be brought into ChemR, which those users will be happy about, and some new research opportunities with a 600 with solids. So that'll be great for a lot of researchers on campus.
Yep.
Okay, well, we'll keep everybody posted about our coming seminar series, and yeah, have a nice rest of your day. Thanks, Michelle. Thanks everybody for your time.
Thank you.
Mhm.